Now, if no question, let's move forward. Now let's look at something called carry select. Okay. Now, so if you say that carry is so important, how about I compute the answer no matter what is the input first. Okay, so what it does is I do the setup as usual, propagation and generation, but I just assume the input is 0. I calculate it first. Also, I put the input is 1. I calculate it first, right? So for example, so this one you have PG. So maybe let's say this is the PG. This one come to here. The same PG come to here, right? Then I calculate this is the propagation bit that the carry out that by assuming either 0 or 1. Okay, just like analogy is like this. I'm going to ask you to have an extra assignment 6, for example, and I say that if you can get it right in 1 hour, or you will get so much score, right? Then what can you do? And I tell you that it will come from any question from the textbook, right? There's one way you can get full score by just doing all the assignment first, 1 week or 1 month before. You do all of them. And then on the day I give you the assignment, you just check, oh, you're asking for assignment 10.5 to 10.10. I just pick 10.5 and 10.10 and submit. Then you can do it within 1 hour, right? If I was asking for assignment 9.5 to 9.6, then you just pick 9.5 to 9.6, right? So it looks like very, very consuming, right? You need to do all of them. But because you get everything done, you assume the input is 0, input is 1, and you make it ready. Then now, if the input is 1, you use this multiplexer to get the output. If the input is 0, you use this multiplexer to pass the 0. Okay, but the carry is very ready. Once I know what is carry in, then I can give you the carry out immediately. That's called carry select. Any questions? Now, how do we do it? Let's take a look. Why it is better? It's actually not much better, but it improved from the carry bypass by 2x. How does it do it? So I have 16-bit here. Again, every one of them do the setup, T setup. Okay, so this is T setup. Now, once I'm done the T setup, remember here comes in the A and B's. So here it generates G and P, but you have 2 sets of hardware. Okay, you are wasting energy and also area. But you see, at this time, all of this block has the carry ready. Whether your carry in is 0 or 1, I don't care. I have it computed already. And then now the carry in, right? If carry in is 1, then I select the 1 carry. If carry in is 0, then I select this one because I already have the answer. So I need to propagate through here, right? But before that, let me also say, when you do this carry, of course, here you have 4 bits, you get M times T carry, right? You do have this propagation. It takes N times T carry to make this ready and this ready. But this block and this block are doing in parallel. Okay, so don't waste any time. Okay, but then you all, of course, then you need to do the multiplexer. This is the T. Let's call it multiplexer. It's just like bypass, T multiplexer, right? So when I'm doing this, these are done already. These are valid, right? Because I already assume 0 or 1, 0 or 1. I don't need to wait for before. They are already. It's just letting the multiplexer to select them. That's why I only need to do N divided by M multiplexer delay. Okay, once I reach here, these are ready already, right? Then I just need to do the final sum. Now you compare with the carry bypass. Okay, this is carry select. You save this one. Okay, you save it by half. Because in the past, I have MT carry plus MT carry, so it's proportional to 2 MT carry. But now this one is only 1 MT carry. Is this clear? Any questions? Maybe let's pause for a few half minutes. Think about it. See if you understand what I mean. Right? Any questions? Everything all right? Now you see here we have 16 bit, S0 to to S15, right? We chop it into 4 bits in each block. And each of them, we have this carry in, carry out, right? So in your design, this can be ground, this is VDD, duplicate this block, right? Then you have a very good performance. And this is the so-called linear carry select, right? Same as previous page. But why do I repeat it? Because here we have a timing diagram. Let's look at this. Let's say I use 1 unit of time to do the setup, right? Then of course, after 1 second, after 1 unit of time, these are also ready because they're in parallel. Same here, after 1 unit of time, these are ready, right? Here is just saying that the BP propagate to a transmitter to this one carry. This one transmitter to CO carry. So they all are ready at the same time, 1 unit of time, T setup. Now then, it will propagate to generate the carry, right? Here, take 4 units of time. From here to here, plus 4. Both of them, right? Same here, plus 4. Because they all do this in parallel. This is a ripple carry, going from left to right, 4 units of time. So because of this, when I reach the multiplexer, it becomes 5. This is 5, this is 5, this is 5, 5, 5. And then we will start doing the calculation. Because this is available at 5, this might take 1 unit of time, so it is available at 6 after this multiplexer. Some delay, right, due to the multiplexer. So this is available at 6, then this is available at 7, this is available at 8, available at 9, and then it's ready at 10. So the total computation time, if all the T setup, T ripple are the same, is 10 units of time. But then from here, you start seeing that there's a waste. Why there's a waste? I am ready at 5 units of time already, but you are still not ready. You are at 6. And even this one is worse. I need to wait for 2 units of time in order to do the computation because you are still at 7. You arrive at 7. This one arrived at 8. I wasted 3 units of the time, right? So that is not optimal for a linear carrier adder. Do you see the problem? They're not a really problem, the inefficiency. You will naturally say that, can I do some computation between 5 and 6 for this guy? between 5 and 7 for this guy, between 5 and 8 for this guy, because we're just sitting there to wait. If I can contribute something, maybe the overall performance will be better. Make sense? And because of this, we come up with something called square root carry select. Again, it's carry select. So what's so different? Let's look at the block compute breakdown. We start with 2 bits here, and then 3 bits, 4 bits, right? 5, 6, 7, 8 is 4, right? 5 bits, 9, 10, 11, 12, 13 is 5, 6 bits. So this is not the same. Here is what? 4 bits, 4 bits, 4 bits, 4 bits. Linear carrier. Square root is 2, 3, 4, 5, 6. Why it's called square root? I'm going to tell you why. But let's see how it will make things better. Okay, after 1 unit of time, we are already set up because they're independent of each other. Then in the carry, here I only have 2 bits. It plus 2 units of time. Plus 2 units of time. That's why it's ready at 3 units of time. This one, I have 3 bits, so it's plus 3 units of time, plus 3 units of time. So it's ready at 4, right? And this one is 4 units of time, 4 units of time. So it's ready at 5. This one, I have 5 bits of ripple carry. So it's 5 units of time, 5 units of time, it becomes 6. And now if you look at the timing diagram, this is ready at 3. Okay, this one come in. It takes 1 unit of time. So becomes 4. Hey, I'm ready at 4. You are also ready at 4. No waste, right? Then it becomes 5. Hey, I'm ready at 5. You are also just ready. No waste. We compute together. Same for this one. And eventually to this one. And then you see all together, I only use 9 units of time. But I'm working on 20 bits. Look at earlier. This is only a 16-bit adder. I use 10 units of time. My 20-bit adder is faster than the 16-bit adder by 10%. That's why this is better, because there's no waste. How do we do the timing diagram, right? Everything is similar, except that here will take a longer time, right? So you can see that if you add the multiplexer together, you will get into this one, square root 2n. And that's why it's called square root square root carry select. Is that okay? Questions? So in the previous semester, some student will actually, this is what I asked you to do, square root carry select. That is what is you are asked to do in the project. So you see that you probably want to have a bit slice, implement the bit slice first, right? And then you have a higher level block. You know how to do the block already in assignment 5, right? And then you construct different block. I think I asked for 20 bits, but I forgot what I asked. So basically, you only need 5 blocks and then implement it. And remember, try to do all the routing in the bit cell first, so that you don't need to do too many routing when you go to higher level, right? When you do the routing well in the first bit, then the rest, you just put them together. They will connect naturally. When you do the layout, your goal is that in the cell, right, you want to abut all the metal to the edge. So you put another cell, they will just connect automatically. You don't need to do a higher level routing. Okay, any questions? Okay, if no questions, then let's take a look at the difference, right? So again, this is ripple. Ripple give you what? Give you n, a slope of 1, or I would say n divided by n, right? Linear select will be better. It will be m divided by n, right? And this one will be square root n, square root of n. Divided by n. No, actually, this one I should not say anything because it is still m, but it is m, but then it further reduced the T mass. Okay, so I'm not going to put the slope, but you can see that it go tail down, so it has a faster speed. Okay, no question. Today is pretty quiet. Okay, so that is the most difficult part in this not most difficult part. I mean, that is what is related to your project, right? So please start working on that. Now, then naturally you will ask, can I even get rid of the ripple effect, right? If you take a look at this, I still have this m carry that I need to take care of, right? I still need to propagate, right? Or here, propagate, right? So is it possible for me to even get rid of it? Yeah, in principle, you can do that. What you can do is just compute the carry using all the inputs. Why do you want to wait for propagation, right? So for example, the output carry out of k equals to if it generates at the kth bit, and then if the kth bit propagates the carry in of the kth bit, right? Remember that the carry in of the k bit is just, right, this carry in of the kth bit is just equal to carry out of the k minus bit, right? Is this okay? So I can continue. I say the carry out of the kth bit equals to the generation of the kth bit and then propagate. And then now I substitute, because the carry out of the k minus 1 bit is just if the k minus 1 bit generates plus the propagation, if the k minus 1 bit propagates, and it propagates the input of the k minus 1 or the output of the k minus 2. Yeah. Again, what is this? This is just the input to the k minus 1. Yeah. So I keep doing this, keep substituting. Eventually, it will be, say, the propagation of the first bit, generation of the 0th bit, plus it propagates it, and then the input of the 0th bit. So carry out is nothing but just a Boolean algebra, right? So here I can just implement that in a big logic. Basically, here is saying that if I get carry, if this is the sum, right? Carry in times the I forgot the equation, right? The carry in and also the P0 will give you the PS, the S1, right? And then same for this one, right? So if we try to put all the all the inputs into a big logic, I'm able to just generate the carry out of this block right away. I don't need to wait for propagation. So how do we do it? For example, this is a circuit to generate the carry out of the whole block. There's no ripple, right? It's not bit slice. We did not put into 4 bits. We just directly take P1 0, P1 to P4, P3, and G0 to G3, and also carry in to generate the carry out. How to read it? It's not difficult. This one is 0 if let's maybe I don't color it, right? So maybe you need to watch my video later. It will be easier. If this one discharge, what does it mean? Can someone tell me if this transistor is on? What is the meaning logically? If this one discharge, what is the meaning of this logic? First of all, why this one will discharge? Why this one will be pulled down to 0? Under what situation would this one become 0? Can someone tell me through this path?
If G3 is high.
G3 is high. What is the meaning of G3 high? Logically, what's the meaning of G?
A and B?
A and B, yes, good. But what I mean, just verbally, what is the meaning of G again? Verbally, what is the English that we
Generate.
generate? Which bit generate? When we say G3 is 1, which bit? G3. I'll tell you, 3, right? The third bit, right? So output, negation of output is 0 if the last bit generates. Make sense? CO3 equal to G3 plus, do you see that? But I also have another path to get low. I can do this also. Now, can someone tell me what does this mean? Just based on the signal. Okay, first of all, how can this path turn off? What signal does it need to turn this off? What signal needs to be 1 to turn this off? I mean, turn this on, I mean, to have this path conducting. The blue path.
G2.
G2 equals to 1. What else? If only this one equal to 1, is it enough? What else? Where does it go through also?
P3.
P3. So what does it mean? It means P3, G2. It means either your second bit generate and the third bit propagate you. Even you generate, I refuse to propagate, you cannot propagate carry to out. But now, because the second bit generates, so, and also the third bit propagates, then I'm going to pull this to 0. This is not, again, not, okay? So it means in making CL3 equal to 1. Is this okay? It has many paths. Let's look at the last path. It can also go through this guy. right? What does it mean? How can I make this on? I need Ci equal to 0, P0 equal to 1, P1 equal to 1, P2 equal to 1, P3 equal to 1. It means that you give me a carry in that is 1. First, P1 need to propagate. The first bit propagate, P0 propagate, P1 propagate, P3 propagate, P4 propagate. Then my carry out will be 1, right? So the whole circuit is telling what? Very logical. My output will be 1. Again, this is negation, so this is pulled down. We add an inverter, becomes the real output, right? My output will be 1 if third bit generate, or second bit generate, third bit propagate, or second bit generate, first bit generate, second bit propagate, third bit propagate. Or you have carry in, many or, you have carry in, first bit propagate, 0 bit propagate, first bit propagate, second bit propagate, and third bit propagate. Then I have carry out. So this is a way, right? We can compute this whole graph. So there is no ripple carry. I know CL3 right away from this P1 to PGs. Sorry, I got disconnected. Where were I when you last hear me? Did I talk about this green part already?
I think you were in the middle of explaining that.
The green part?
I believe so.
Okay. Yeah. So maybe I talk about the green parts one more time, right? So this is the another possible path that can bring the CL3 equal to 1. Here is bar, that's why it's 0, right? So CL3 is 1. This path is telling us that if the input is 1, P0 is 1, it propagates. Second bit, first bit propagate, second bit propagate, third bit propagate. Then my output will be 1, right? So very logical. You have many possible paths. And I can get this expression by just keep expanding. Okay, so there will be no ripple carry delay, right? If I have 4 bits, I calculate all them at the same time. I have 128 bits, I calculate at the same time. I don't need to wait for it to propagate one bit 1 to 128, and then know that I need to have a carry out. Is this okay? But this becomes a problem if it becomes too large. For 4 maybe still okay, but it already very bad. Why? Look at this. How many parallel branch do we have for the output? Right? I don't know if you can see clearly. This is the output. What determines the output capacitance? Do you remember the intrinsic output capacitance? And just now when I talked to another student, she's not very sure about how to find the p-value. P-value, I put in the solution, but maybe not clear. But to find the p-value is that you size the transistor so that you have the same resistance as the inverter, and then find the drain capacitance, right, as the intrinsic capacitance. The drain capacitance depends on how many transistors you connected to the output. For example, in the midterm 2, in your bottom, if you size it, your bottom have 2 NMOS connected to the output. That's why your capacitance contributed by the NMOS is 2 plus 2. And at the top one, you have 2 PMOS, it is 4 plus 6. I forgot the exact number, right? But you add them together. Same here. How many capacitors going to connect on this output? You just count it. How many drain are connected to this? 1 PMOS, 2 PMOS, 3 PMOS. Oh, sorry, some problem again. Right? 1 PMOS, 2 PMOS, 3 PMOS, 4 PMOS, 5 PMOS. And then another 1, 2, 3, 4, 5 NMOS. Right? So you actually have 5 parallel branch. What is the problem? Which is means n plus 1, right? Depends, right? N plus 1 equal to 5, where n is the number of bits, right? I have 4 bits, I have 5 branches. What is the problem again? I kind of told you already. What's the problem of having n transistor connected in parallel to the drain capacity, to the output? Forgot? What is the delay? Can someone tell me? Just tell me. How do you compute the delay of a gate? We just done the midterm 2. What is the equation for the gate? Remember, T equal to what? TP0 times what? Times P plus, I think I need to test you again in the final. FG divided by gamma, right? And P is related to what? The intrinsic delay, intrinsic capacitance, right? Every gate has an intrinsic capacitance, which is a function of the drain capacitance. So if I have 5 of them connected in parallel, then I have really huge drain capacitance. This delay is going to be large. Is this okay? How many transistors do we stack in this case? Again, n plus 1, right? Because I need to go through this and logic. So what is the problem of stacking 5 transistors? Can someone tell me? Think about delay. I know you know it. Just imagine this is an interview. Then you will be able to answer. What's the problem of making it stacking with many transistors? I cannot hear someone try to answer. But try to correlate to what we have learned before, right? Again, it's because you have a large resistance when you have this Elmore delay, right? You have it increase the resistance, but not just this. It has the Elmore delay. Remember that? And remember, we have this internal resistance every place, and it's not small. You have 2 transistors. This is a big cat. This is a big cat. This is a big cat. Again, this is a big cat, right? So the Elmore delay is actually proportional to n squared. It can be proportional to n squared, the delay. I mean, not resistance proportional to n squared, but the delay proportional to n squared. right? Because you also have the capacitor. Yeah, so that you cannot say I have 128 bits. I just dump everything together and implement this logic, and hopefully I can get the carry in immediately. Since you scale with n squared, and then you have such a big intrinsic capacitance, it can be even slower than ripple carrier if you don't do it well. Okay? But this is carry look ahead. For 4, maybe okay. Okay? So what can we do? We use something called logarithmic look ahead adder. Okay, so that is what I want to discuss. But before that, we need to learn some terminology to make the life easier. For example, if I have a bit, right? We already understand the carry out of the 0th bit is if you generate in the 0th bit, or you propagate in the 0th bit and you have a carry in that is 1, right? We can say that like you are rich, either you generate a lot of money, or your parents give you money and you keep it, right? If you don't keep it, even your parents give you a lot of money, you won't be rich, right? So this is all condition, right? Then how about the second bit? We already discussed either the first bit generates or the first bit propagates, and then you have carry in. But carry in is just what? This is CO0, which is equal to CI1, right? The in carry into the first bit is the output of the 0th bit. Then we can expand it to this. What does it mean? What does it mean here? Basically, you can group it into 2 groups. This one is basically saying that the 2 bits as a whole, right? You have 2 bits generate. Right, isn't that? Either the first bit generate or the either the second bit, a bit 1 generates, or the bit 0 generate and then the bit 1 propagates. They make it as a team, like a project team. This is just representing the whole team generate, right? It doesn't matter who generate. As long as eventually it goes out, that will be okay. It's just like saying this. This is a group, right? 2-bit group. You have bit 0, you have bit 1, okay? It's just saying that I have output CO1. Why? Either I generate or you generate and pass to me. You generate and then I pass to the output, right? Then that is just the whole group generate. Similarly, for this one, it's just saying that the 2-bit group propagates, right? You need to propagate because first bit has to propagate and second bit has to propagate. Then the whole group propagates, okay? And that's why we can label it as G1 to 0, means that this 1 to 0 bit, the whole group generate. P1 to 0, the whole 1 to 0 bits propagate, right? And this is very logical, right? The 2-bit has a carry out if this group generates or this group propagates and we do have a carry in, okay? And similarly, if I say the third bit, this is 4th bit, but bit 3, it has a carry out if bit 3 and bit 2 generates or bit 3 and bit 2 propagates and the input to the second bit is 1. Okay, so if you break it, you see this is like G32 is just G3 generates, bit 3 generates or the bit 2 generate and bit 3 propagates. Then the whole team generates and this is the propagate. Okay, and then we introduce something called dot product, just a notation. So what does it mean? It's just saying that okay, I have 2 bits, right? B3 to B3 means this is just 1 bit, bit 3, right? This is just equal to G3 and P3, okay? So these two things, I put them together, is just the same as this notation, okay? It's just saying that B3 and B2 propagate is equal to the propagate, and then you will do G33 plus P33 times G22. That is the dot product of this notation. So basically, it's just saying that if put these 2 bits together, it's just equivalent to B3 generates, the 2 bit group 3 and 2 both generate or propagate. Right? I should say this, right? You have 2 bits. This one, this is bit 3. This is bit 2, right? And then I say this bit is called G33, P33, right? It has some property. We don't know whether it's 0 or 1. Okay. And then if you put them together, the whole thing, the group, this is called bit 2 to 3. The whole thing is just like it becomes G32, P32, which is equal to G33 plus P33, G22, P33, P22. That is what we're trying to say. So if you have 2 bits here, right, you combine them as the whole group, then to label it, it becomes P32 means that the group of bit 3 to bit 2, and then we have generate and propagate, and to calculate the generate, we use this equation. To calculate the propagate of this whole group, we use this equation. Okay, so I'm a little bit too slow, but why I introduce this? This is the logarithmic look-ahead. Instead of putting everything together, we try to decompose it in a binary tree. That will save the logic. It won't be so bulky. Okay. For example, we can take this term, this one, right? How do we calculate this one? We say we take this one by taking the output of this one and this one. But when we say output of this one is, our goal is to find C70, right? The seventh bit. But this one will be the C40. But this C40 will depend on the other group. We keep breaking down. Like this. And by doing so, we can make the logic simpler. You see that I break them all into the final destination, every bit contribute, but they build up as a logarithmic look-ahead header. I will talk about this next time, okay? That's it for today. Any questions?